the area. Here in this section, we kind of go back in time to try to give a preliminary understanding of what the integral actually is. The integral is the computation of the area under a curve. The curve that is examined is set to be broken down into thin rectangular slices that we call partitions. And you take those partitions, those slices, rectangular slices, you make them as thin as possible with the limit process, and then you add or sum up all of these rectangles. Well, that summation is necessary to understand the sigma notation for the summation. And then from there, we can establish a foundation to finding the area under the curve of a particular function. So first, the sigma notation, excuse me. Here, the summation of n terms. Here, the terms are no more than just the sequence of values. So a sub I, as I goes from 1 to n, we add up those terms, and we call that the summation. Uh, a an idea of some summation formulas. Here, 4 of them are given. If you sum up a constant, if the number is 5, 5 taken n times would be 5 plus 5 plus 5 n times, or just c times 5 times n, or c times n. If we're adding numbers from 1 to n, add them up, 1 plus 2 plus 3 plus 4 plus 5, and so on. You add those up. Actually, what that is the number of n terms times n plus 1 divided by 2. And typically we prove that one to give you an idea of what's going on. It is understood that it was Carl Friedrich Gauss at the age of, some writings say he was about 7, some say he was about 9 or 10, but his father had given him some math work to do to take the young lad's attention while the father worked on his work that he was working on. I think his father was dealing with insurance acquisitions and actuary information. And back then they didn't have computers, and so his father was trying to compute a lot of numbers, a lot of data over a large period of time. And so young Carl was uh, um, kept asking his father questions, and so the father gave him the task of adding up all the numbers from 1 to 100, 1 plus 2 plus 3 plus 4 plus 5 to 100. And to his dismay, in a matter of no more than about a minute or two, I think even less than that, the young lad called Frederick Gauss had given his father the summation. And so basically what the boy had done was, in essence, to say 100 times 101 divided by 2, and he was able to get the number. And so the father checked it, and it took him, some time to get it, and the young lad was right. So the proof that is given for number 2 is actually the proof from Carl Friedrich Gauss. We know of Carl Friedrich Gauss, the one who has proven for us the fundamental theorem of algebra. Well, the area of a plane region. Our objective here is to understand that the integral, it is the area of a function's curve, the, the area under the curve. Here we want to compute the area or the integral by using the definition for the so-called area, which would be the definition for the integral itself. So to accomplish this task, we start with the preliminary concept of the integral. The integral is computed by summing up thin rectangular slices of the area, using the limit process, forcing the rectangles to be as thin as possible and ensuring that the tip parts of the rectangular slice is a point on the curve. So through the process of summation, we're able to get the area under the curve. Thus, that gives us the integral. Let's see here for an example. Here you want to compute the integral of negative x squared plus 5. as x goes from 0, it looks like it's going to 2. And so to do that, we take these rectangular slices. And the problem is that you end up with some of these rectangular slices being above the curve, some being below the curve. And so the goal then is to make the rectangular slices as thin as possible. The width would be delta x, thus we would get dx for the integral. And to ensure that the tip of the rectangular slice is actually a point on the curve. So to ensure that the rectangular slice, the tip of it, the height of it, is actually a point on the curve, we talk about upper and lower sums. First, we take the function f of x. We take a partition, and these partitions are equally divided. We call the partitions delta x. Delta x is b minus a, where a and b are the interval of which the area is to be computed upon. And n would be the number of rectangles, the number of partitions that you have. And so we say that the minimum value of f of x in the ith subinterval is said to be f of little m sub I. So some minimum value. And then f of capital M of x is the maximum value of f of x in the ith subinterval. So obviously what we want is in between. It's going to be a number in between that. So we said that the area of the inscribed rectangle, that's this guy, is less than it's going to be less than the area of the circumscribed rectangle, which is these rectangles here. But what you want is going to actually lie right in the middle of that. We're going to call that the number c sub I. And so c sub I would give us a number that's going to be on the so-called curve itself. And so here, little s sub n is said to be the summation based on the lower sum, and capital S sub n is said to be the summation of the upper sum, so one from the inscribed rectangles and the other from the circumscribed rectangles. Thus, what you want is somehow sandwiched in the middle. We can get what we want by taking the limit and forcing this by the squeeze theorem to yield the actual area. So we have the limits of the upper and the lower sums. Just take the limit of little s sub n, and then to get the upper sum, we take the limit of capital S sub n. By the squeeze theorem, we can force by the limitation process that we get the same limit. Thus, the area in the middle must be the same as well. And so we give now the definition for the area of the region of the plane. That is the area under the curve. Let f be continuous and non-negative. We're talking about the area, so you want that value to be positive. The area of the region bounded by the graph of f, the x-axis here, the vertical lines x equal a, x equal b, is said to be the area. It's the limit as n goes to infinity of the summation of I as I goes from 1 to n of f of c sub I. The c sub I is what we want. Again, it lies within the center, and it gives us a point f of c sub I, a point on the actual curve, times the thickness. So basically, we're computing the height times the width to give us the area. So c sub I is in between x sub I minus 1 and also between x sub I. Now, how do you get c sub I is the question. Most important. C sub I can be gathered by either this left endpoint or the right endpoint. And what we do here, I think, which is a little bit easier, is to get C sub I as the right endpoint, and I stated here, we use the right endpoint to get C sub I. If you use the left endpoint to get C sub I, then it looks like A plus I minus 1 times delta X. So this is the left endpoint and this is the right. I think the work is a little bit cleaner by using the right endpoint, and so that's the one that I prescribe to you. So the steps that I've given: determine delta x. Recall that delta x will approximate dx. Use the right endpoint for C sub I, and so you're gonna try to calculate then f of C sub I, and then it's going to be times delta x sub I, and that will give us the area. And I say it's approximate because we take the limit of the summations in front of that to get what we actually want, and that's what's given here in this definition. This comes out to be, believe it or not, the integral from a to b of f of x dx. This is the definition for the integral. So we're going to follow our steps there. Write the area using the limit definition. What definition is that? It's this definition here. You're going to do some simplification. You're going to have these I terms in there, I or I square or I cube. That's what's given up here above in terms of how to compute I. And use those formulas there. Here, the summation, this is a tricky part. The summation of a constant alpha is going to be n times alpha. Where does that come from? That's that summation, that first definition here. So the summation of a number is going to always be n times that number. So that's tricky, but I thought best to put that in there. And the book explains it in a very vague way. Simplify, take the limit. Let's see. So here they want us to simplify this just using the formulas. So this is the limit as n goes to infinity of the summation as I goes from 1 to n. And this is 24 over n squared Now, why am I writing this very same thing out again? Times I, if you will. Now, I will become n times n plus 1 divided by 2. So here, we write this as the limit as n goes to infinity of 24 over n squared, and then this is times n plus 1 divided by 2. What happened to the summation? Well, the summation of I is exactly n times n plus 1 divided by 2. So no more summation. The summation of I gives us the result n times n plus 1 divided by 2. So this is, yes, the limit as n goes to infinity. Now 24 divided by 2 is just 12. And here we have n squared plus n. And that's all over n squared. And you can simplify that. It's the limit as n goes to infinity. This is 12 times here 1 plus 1 over n. Now, the limit of 12, the limit of a constant is a constant, and the limit of 1 over n, or 12 divided by n, is 0. So this part here is 0. So we have left the limit of a constant, which is a constant 12, and that's the result. All right, let's simplify this. The limit as n goes to infinity of the summation as I goes from 1 to n. This is 1 over n cubed. Simplify this. This is I squared minus 2i plus 1. And so here, this gives us the limit as n goes to infinity. Take the limit now. We're ready for that. This is 1 over n cubed. Just brackets 1 over n cubed. Now in parentheses, I squared is n times n plus 1 times 2n plus 1. That's over 6. By the formulas up above, minus 2 times I, but I is n times n plus 1 divided by 2. Now this is the summation of 1. So taking the limit of that and the summation of 1, taking n times is 1 plus 1 plus 1. How many ones do you have? You have n of them, so this is plus n. That's the part that you got to watch out for. So now we simplify. It's the limit as n goes to infinity. Now let me tell you, if you don't want to have to go through all the simplification, if you can see what's going on, you can get the answer. Up top, you're going to have the biggest term we call in computer algorithm science, the big O, the biggest contributor for the function that everything else somewhat tails behind. So the strength of this fraction here is 2n to the third. That's divided by 6n to the third. That limit would be 2 divided by 6 because n to the third divided by n to the third, you have the same powers. So the limit or the horizontal isotope becomes the ratio of the leading coefficient. So 2 divided by 6 is 1/3. You come over here. This is 2n squared divided by well, the 2's cancel out. This is just n squared divided by n cubed. You get 1 over n. That limit is 0. Then over here you have n divided by n cubed. That's 1 over n squared. That limit is 0. So the limit here is just 1/3. Well, we'll do the work so you can see it. So this is, up top is 2n. Going to FOIL this and then multiply by an n. This is 2n to the third plus 2n times 1 is 2n, then plus n is 3n, and this is n squared. Then plus 1 times n is n. This is over 6. Plus, this just becomes, that's minus sign. So this is minus, I got the n to the third right there. Sorry, n to the third. This is minus n squared minus, that minus is carrying through, minus n all over n to the third plus n over n to the third. Okay. So this is the limit as n goes to infinity. Let's do the simplification. This term here divided by 6n to the third is 1/3 plus 1 over 2 to the n plus 1 over 6n squared. This is minus 1 over n plus sign, negative sign, so we understand that. And then this is minus 1 over n squared. This is plus 1 over n squared. Now, taking the limits, this limit is 0, the limit is 0, that limit is 0, that limit is 0. Hello, 0. Hello, darling. Too thick. So the limit of this constant here 1/3. The answer is 1/3. All right. So we run the same game. I'm going to simplify that. I is the question. This is the limit as n goes to infinity. Brackets. I got that 2 over n sitting there. This is times the 1. That's the constant term. This is n plus the I is n times n plus 1 divided by 2 times n. So this is the limit as n goes to infinity. Here we have the 2 over n times n is 2 plus this 2 divided by that 2 cancels out. We have n squared plus n, and that's divided by n squared. The limit as n goes to infinity. Well, that constant stays the same. The limit of a constant is a constant. This is plus n squared divided by n is 1 plus n divided by n squared is 1 over n. We know that 1 over n, that part goes to 0. So we're left with our answer 2 plus 1 is 3. Okay. Well, here they built the result n for us, and all we're doing is just simplifying. What if they give you just a function and they want you to build by the definition the area and then compute the limit? Let's see. So here we need the partition delta x. Delta x is said to be b minus a over n, where b is 1, a is 0 divided by n. So our partition will have the width of 1 over n. And what about the value c sub I? What is c sub I doing? C sub I is trying to give us x sub I. So then we can compute the function value, right? So here we said take c sub I to be a plus I times delta x. Well, a, look, I want to say the same thing. This is the interval from a to b. So a is 0 plus I times delta x. Delta x is 1 over n. So this is I divided by n. So now the area is said to be the limit as n goes to infinity of the summation as I goes from 1 to n of the function f of c sub I times delta x. And I just put the sub I there to let you know that we're looking at that, per iteration, but it's the same magnitude, the same width. So this is the limit as n goes to infinity of the summation as I goes from 1 to n. And the function is this negative 4x plus 5. So this is negative 4, but x is I over n, right? That's the c sub I. And then this is plus 5. Now what about the thickness, delta x? Well, delta x is 1 over n. Right. So now this looks like the previous problems. So now we find the limit. It's the limit as n goes to infinity. If you see what's happening, we can go ahead and compute, because the key is that this I, the summation of I, is n times n plus 1 divided by 2, and the summation of 5 becomes 5 times n, right? So I'm going to do brackets, and this is 1 over n times parentheses negative 4. I'm going to say over n. This is negative 4 over n right here, times the I. The I is n times n plus 1 divided by 2. This becomes, look, we took the summation out, so this is 5 times n. that 1 over n, that thickness, is times the entire function f of c sub I. This is the limit as n goes to infinity. I'm going to simplify all of this. So this up top, I have this negative 4 divided by 2, so it just gives me a negative 2. And I get, this is n squared plus n, and that's over n squared. And then this is plus 5n divided by n. This is just 5. Okay. So this is the limit as n goes to infinity. And up top we have negative 2. Kind of just simplify that instead of going through this step, that step. So this is negative 2n squared divided by n squared. It's just negative 2. So this is negative 2. And then this is negative 2 times n divided by n squared. So this is just minus 2 over n plus 5. Now, the limit as n goes to infinity of negative 2 over n, this part here goes to 0. I have left negative 2 plus 5, just get 3. Okay. One more here. All right, so delta x is 1 over n. C sub I is the 0 plus I times 1 over n. So here I get 1 over n again there. What helps me is that we start at 0. If not, we get a number plus the 1 over n. And so now the area is the limit as n goes to infinity of the summation as I goes from 1 to n. This is the partition, the thickness, that I over n. Excuse me, is 1 over n, the thickness. So 1 over n times the function, which is x squared. So that's going to be the I over n to be squared plus 2. And so, let's see here. Hopefully this will work. Okay, so let's continue. Let me write this a little bit better. I think I was using brackets. So the function f of c sub I, so this becomes I over n, which represents the x that's to be squared plus the 2. And we got the thickness. I just put the delta x right there. So this is the limit as n goes to infinity, the summation as I goes from 1 to n. We have this 1 over n sitting there. I'm going to simplify there. This I square over n square plus 2. So now I think we can go ahead and sum it up by using our formula. So this is the limit as n goes to infinity. We have 1 over n, and this is times, now that I square is n times n plus 1 times 2n plus 1 divided by 6. And then this is plus 2. So that gives us the limit as n goes to infinity. I missed my n square there. I need to put that back there. Can't forget that. So we're gonna run the 1/3 through. Oh, and this times n. You drop the summation. This is 2 times n. That'll mess us up. So up top here, I have 2n to the third, 3 n's, so 2n to the third plus, this is 3n, just 4n, then times the n. So this is 3n squared plus n, and that's over 6n squared. 6n to the third, at n downstairs. Can't fix that like that. To the third. And this is plus 2n divided by n is just 2. So we simplified. You see that the answer would be the 2, 6, which is 1/3 plus a 2. Let's see. This is the limit as n goes to infinity. This is 1/3. Simplify that. Plus, looks like 1/2 n, and then plus 1 over 6n squared plus a 2. This limit is 0. This part is 0. We have left the limit of 1/3 plus 2. It just gives us 7/3. That's it. Thank you.